Hey everyone, so we are going to begin our unit on chi-square tests. Um, I think the order your textbook did this in is really interesting because I personally think that chi-squares are much easier both to understand and to calculate than all of the t-test, ANOVA, regression stuff that we've been doing thus far. Chi-squares logically make a lot of sense. So your textbook actually does a really great job of explaining the calculations of them and the procedures of them. I feel like the introduction to them gets a little word salady in some places. So the way we're going to do this is I'm going to explain what chi-squares are and when we use them. We're going to walk through a couple of examples by hand, and then we will put it into PSPP. Chi-squares are actually really easy to calculate by hand. They're one of the ones I don't mind doing pen and paper. So what you're doing with a chi-square, and some people say chi-squared with a D, same thing, no difference. And the symbol is like your fancy swirly X, which is the lowercase chi, and then with a squared sign. So this is chi-squared. The question we're answering with chi-squared is ultimately, do the numbers in my groups split the way I expect them to? And here's what we mean by that. When we're dealing with chi-squared, the defining feature is that our variable of interest is a nominal variable. By this point in the semester, hopefully you know what that term means off the top of your head. But if you need a refresher, remember, a nominal variable is something that you are naming your answer. What race are you? What religion are you? Where do you work? Or what line of work do you work in? Things of that nature. What neighborhood do you live in? It's a nominal variable. It's nominal. We can obviously, as we practice doing this semester, put it in our software and code it and assign it a number. But at the end of the day, the answer is not something that I can give you numerically and mean something, right? I'm naming it. Now, thus far, everything we've talked about, unless we code our variables, we can't really do anything with that. Let me silence this so you don't hear my beeping in the whole background of this video. We can't really do anything with that. A chi-square allows us to deal with nominal groups as our outcome. But its utility, again, is looking at, do the numbers in my group split the way I expected them to? If I'm expecting an even split between male and female students, and that is my variable of interest, right? Is male and female students. Or if I am looking at, well, we'll jump into this example because it makes a lot more sense once you see an example. What we're doing is we are taking what we expect and we're comparing it to what we observe or our actual data. All right. Let me lay out an example that's going to make this easier to understand. Let's say there is a small office, it's a sales office, and their office policy is that anytime a potential new client comes in, that the two primary sales agents, Sal and Sue, are supposed to get potential new clients split up evenly. The new client calls, the front desk person answers the phone, somebody says, I want a quote about something, or so-and-so referred me, and that the front desk assistant is supposed to evenly split those new calls between Sal and Sue. I expect to see a 50-50 split for Sal's new calls and Sue's new calls. What I would be doing with a chi-square is I would be going in and I would be looking at the actual split of those calls, the actual distribution, the actual frequency of those calls, and comparing the new clients that were forwarded to Sal and the new clients that were forwarded to Sue, and see if they're split 50-50 in the same way that I expected them to be. This is what we're doing for a chi-square. Our variable of interest is a nominal variable. Were you assigned to Sal or were you assigned to Sue? Okay, it's a nominal variable. I'm not interested in the mean of anything. I'm interested in the number of clients that each one got in their time period of interest and how that lines up with our policy. Let me give you another example before I actually start putting some numbers on here, because sometimes understanding the theory behind what we're doing is the hardest part. Um, let's say, and you can be comparing it to an already known proportion, and that proportion does not have to be a 50-50 split. So let me back up one step here. So in the hypothetical example I just gave, right, it was splitting 50-50. It does not have to be split 50-50. Maybe Sal works part-time and Sue works full-time. So naturally, we're going to expect Sue to get more calls. So let's say what I'm expecting, what I want to see, is Sue gets 75% of the new calls and Sal gets 25% of the new calls. Maybe I expect it to be divided up that way because Sal only works part-time and Sue's full-time. So it doesn't have to be a 50-50 split. It can be any proportion that you're dealing with. And that proportion can be compared to whatever it is that you're wanting to compare it to. So, for example, let's say that I know the nationwide data of the percentage of graduating high school seniors that are going to be attending college that are planning on being a STEM major, right? Science, technology, engineering, math. I know the numbers. Let's say that I'm totally making this up. But let's say we have nationwide data on this, and I know that nationwide 20% of graduating high school seniors that are attending college are planning on being a STEM major. That's my nationwide number, is 20%. So 80% would be non-STEM, right? Let's say that Central High School has recently received a grant to try to get more teenagers, high school students interested in STEM. And so they've been able to hire some new instructors and offer some new courses and send their science and math teachers to these nationwide conferences on how to get students interested in science and math. And they have all these amazing teaching strategies. And that we're starting to kind of, some of the local colleges are reporting, hey, students that are graduating from Central, we're getting more like science and math majors, STEM majors from their graduates. So maybe I want to do a comparison, and I want to do STEM and non-STEM. And maybe I want to say, okay, I know nationwide 20% of graduating high school seniors that are going to college are saying they're going to be STEM majors. Let's say I want to compare Central High School graduates. And I want to look at what percentage of them are comparing STEM and non-STEM. And so my expected, based on my nationwide average, would be 20%. And I'm going to see 20% for STEM, 80% for non-STEM. And I'm going to see how that compares to my actual. All right, so that is what we're doing here. The variable of interest, the nominal variable, would be their declared major. That is a nominal variable. What major are you? Okay, it's not a number, it's a name. Again, I'm not interested in the average of anything, right? And that example may have perked your ears up, right? That might have sounded familiar, because if you're thinking, oh, wait, I'm comparing a sample that I have to a nationwide population, this is sounding a lot like a one-way t-test, and you are absolutely correct. The difference is here, we're not interested in comparing the mean of anything. We're not averaging anything. We're interested in the count of the nominal variable, okay? Hopefully that makes sense. If that is confusing, I'm happy to do a whole little mini lecture on the difference between a chi-square and a one-way t-test. So if you're having a hard time with that, email me and I will explain that further. So my variable of interest is a nominal variable. I'm interested in the count of that nominal variable. And if the count matches what I'm expecting based on whatever standard that expectation is, okay? Hopefully that makes sense. Hopefully I did not word salad that as in a way that made it more difficult than it needs to be. One other important thing to know is that this does not have to just be two. I could list 5 salespeople and say we want to split it up. We expect each of them to have about 20%. I could compare every major. So I could compare STEM with behavioral social sciences, with arts, with, and I could have, this is not limited to 2. We're going to keep it at 2 for now because it makes the math a lot easier to explain, but it does not have to be 2. So this is the basic of what we are doing with our chi-square. So the next important thing to note is, what is our null population when we're talking about a chi-square? Our null. It's been a long day. Our null hypothesis when we're talking about a chi-square, not null population. Our null hypothesis when we're talking about a chi-square. Our null hypothesis is that there is no significant difference between the expected groups, or the expected numbers, and the observed numbers, or the actual numbers. So null hypothesis, there is no significant difference between expected and observed beyond what you would just expect by chance, right? Because if I expected nationwide, to go back to the STEM example, if I expected nationwide to have 20% of graduating seniors entering college going into a STEM major. Let's say I had 100 students graduating from Central who were going into college. And let's say I have 22 of them that are going to be a STEM major. Excuse me. Is that 2 more than what I expected? Is that significant, or is that maybe just due to chance, right? I mean, it's 2 students. And that's what we're going to get into calculating. So our null hypothesis is there is not a significant difference between the expected count and the observed count beyond what could just be explained by chance, by coincidence. And then obviously our research hypothesis, depending on what we're researching, is that the distribution of whatever it is we're looking at, the distribution of our clients, the distribution of our students, is different than what would be expected. So null, no difference. Research, difference. Really similar to everything we've been doing thus far this semester. So let's actually fill in some numbers here and see how this works out. So we're going to go with our Sal and Sue and expected clients, okay? So let's say that, and I'm going to use this to make a contrast. Let's say that what we ended up with is we found that at the end of the month, there were 20 total potential new client sales calls that came in. So what we would expect is that 20 would be split 10 to Sal and 10 to Sue. Okay. Now, we go through and we look at our records and we find out that 18 went to Sal. Horrible 8. 18 went to Sal and 2 went to Sue. That's still a horrible 8. Okay, 18 went to Sal and 2 went to Sue. We would assume this is probably going to end up being significant. But this brings up the next argument, though. So we know that we are 8 different than our expected, right? Because with a chi-square, our starting point is always going to be that we are going to subtract, and let me double check which direction we subtract. It doesn't matter because we end up squaring it anyway. But our first step is always that we subtract the expected from the observed. So what we see here, okay. So we subtract expected from observed. So we do O minus E. So right here, O minus E would be 8, and O minus E would be negative 8. So our difference between our expected and observed is 8. And this will always be proportionate when you're dealing with just 2, right? Because one's going to be above and one's going to be below. Now, this 8 difference, before we can move forward in calculating any sort of chi-square or determining whether or not this is significant, we need to know more than just what the difference is here, right? We need to know just how big this expected number is. Because if I'm dealing with 8 difference, 8 and negative 8, analyzing a breakup of 20 clients, yeah, 18 compared to 2 is pretty significant. But let's say I was analyzing 5 years worth of new sales calls, and there had been 2,000 of them. And so let's say this number I expected that to be split up as 1,000, if I can write today, and 1,000. And let's say Sal had ended up with 1,008 and Sue had ended up with 992. I would still have 8 and -8 in this example, right? But in the grand scale of 2,000 phone calls, being 8 off from a 50-50 split, this is now going from, okay, the front desk person is clearly showing favoritism in who's getting the sales leads, and wow, over the course of 5 years and 2,000 phone calls, you were only off of a perfect 50-50 split by 8. Like you deserve some sort of accuracy award, right? So obviously the number that we're dealing with of our expectation plays a huge role in determining how significant this number is. And so that's what we're going to be looking at as we move forward with our chi-square calculations. So I'm going to stop this video here. I'm going to reset the board, and we're going to talk about the math of how we actually do this.